All right, it's my pleasure to introduce Dmitri Sorokin. So he's going to talk about how SYM domain walls look like. I guess super young Mills, note it down.
Thank you very much. I'd like to thank Hisham first for this invitation to participate in this nice and exciting workshop and in such an exciting place, and would like to present work which I did in collaboration with Igor Bandas and Stefan Alanza, who was PhD student in Padua last year. And the main goal of the talk, as the title says, is to present the shape of domain walls in pure n equals 1, d equals 4 super-Young Mills with the gauge group SYM. So I will concentrate on SYM group, though the results can be extended to other gauge groups. We will work with the simplest super-Young Mills theory in 4 dimensions, which is known since '74. And during these 45 years, there has been an intensive study of these simply looking theories, and quite deep and non-simple structures were discovered during these years. And for example, in the early 80s, it has been it became clear that this n equals 1 super-Young Mills with the SYM gauge group has n-degenerate vacua, supersymmetric ones, which are distinguished by the vacuum expectation value of the Gagina condensate, and which are related by the discrete ZN symmetry here. So the Gagina condensate looks as follows. There is a dynamical scale at which the Gagina condensate is formed, and then there is this phase which is discrete. It depends on the discrete parameter n running from 0 to n minus 1 divided by the this dimension n of the group SUN. And then it took some time to realize that since there are n different vacua, then there should be domain walls, BPS domain walls, which interpolate between these different vacua. And Dwali and Schiffman, on the general grounds, proposed that the tension of these domain walls should be proportional to the modulus of the difference of the values of the Gagina condensate for different vacua, for example, the vacuum N and the vacuum L here. And then there has been, since the 90s, there has been a lot of activities on the domain walls in this theory and in its extension to super QCD. And these activities were carried out from different perspectives and with different approaches. And one of the recent reviews on the subject is by these BBB people. And it is from this paper, actually, that I learned that there are some issues still which are still there as far as the domain walls are concerned, and this paper attracted my attention to this subject. So, for example, the issue is that if we would like to consider these domain walls as solitonic solutions in an effective field theory describing the low energy behavior of super-Young Mills theory, then until recently the form of this solitonic solution has not been known. And the reason for this is that, as we will see, the supersymmetric domain, super-Young Mills domain walls are not smooth solitonic field configurations. Their existence requires the presence of a source, which has been lacking in the pure Young Mills theory. And turns out that these sources are dynamical membranes. So what I would like to show is that how to couple the dynamical membrane to n equals 1 super-Young Mills and to its effective description in terms of the Veneziano-Yankelovich Lagrangian, and then to show how these membranes create BPS domain walls and what the shape of these domain walls is. So let me start from the very well-known facts about the pure n equals 1 super-Young-Mills theory, just to set the stage and to see how to resolve this problem of domain walls. So we will deal with the vector multiplet in the joint representation of SYM, where A is the gauge field, lambda are the gaugini, and D is the auxiliary field of this vector multiplet. The index I is the joint, which I will skip everywhere in my talk here. And then the building block of the super-Young-Mills Lagrangian is also very well known to be a spinorial chiral superfield of this form, which contains the gaugina field, the auxiliary field, and the field strands of the vector gauge field here. And in terms of the in the superfield formulation, the Lagrangian looks as an integral of the chiral superspace of the trace of the W alpha, which is, of course, very well-known things. Now, let's have a look at the form of this trace of W alpha. One can see that this is, again, a chiral superfield, which has the following structure. So the leading component is the trace of the lambda, which may be then associated, whose vacuum expectation value may be associated with the gaugina condensate. Then there is this colorless fermionic field chi, which is composed in this way from the fundamental fields of the gauge multiplet. And there is this F field, which is would be auxiliary field if this S were the conventional chiral superfield. And this F term has the following form. And of course, we well know that it is a complex superfield whose real part is just the super-Young-Mills Lagrangian, and the imaginary part instead is the topological density. And this will be important for us. So if you take the imaginary part of F, this is not a scalar basically, but the dual of a 4 form, which is the D of the Chern-Simons term here. So I will call it star D C3, calling C3 this object here. So what we learn from this is that this chiral superfield actually is special one. So it's not the standard one where F is the complex scalar, but it contains the 3 form entering as the field strength, with its field strength here. And these superfields were first introduced by Gates in '81, and he noticed that these kind of superfields, chiral superfields, are constructed using the real prepotential U instead of the complex prepotential which one would use to solve the chirality constraint here. So, and this is one of the important points which will play the role in this construction. Now, let me remind quickly what's going on with the vacua and of this theory and with the fate of R symmetry. So at the classical level, this theory has the R symmetry. This is U1 R symmetry, which rotates the fermions lambda, but it's anomalous so that the conserved current is normal conserved due to chiral anomaly, and the chiral anomaly has this structure here, where it is, one can see this coefficient 2n here, which distinguishes the chiral anomaly of the fundamental representation, where there would be 1 here instead. But here we are dealing with the joint representation, with the fermions in the joint representation. So there is this factor here, 2n, and this means that U1 is not broken completely, but it is broken down to the Z2n discrete subgroup. But then, as I have already mentioned, at the beginning of 80s, people realized that this discrete part of the R symmetry is further spontaneously broken by the Gagina condensate here, which was for the first time computed using the instanton calculus by Novikov and Schiffman in '88. Here. So, this is how we get the Gagina condensate, and which describe different vacua of this theory. Now, I would like to, as I said, to find solitonic solutions of domain wall types in the theory using an effective Lagrangian formulation. And this is provided by Veneziano and Yankelovich Lagrangian, which I would like to revisit now. So this Lagrangian provides the description of colorless bound states of the super-Young-Mills multiplet, the gluables, gluinables, and their fermionic partner. And it shows quite, in a quite simple way that there is a gluina condensate and how the degeneracy of the super-Young-Mills vacuum arises. So to construct the Lagrangian, we use, again, this special chiral superfield, where now this scalar chi and the auxiliary field sector are considered as independent, or fields not composed of the super-Young-Mills theory, but we should keep in mind that they come from the super-Young-Mills theory. So again, for simplicity, I will often use, instead of the 3 form, I'll use its 1 form dual calling or vector CM in the description. Now, the Veneziano-Yankelovich Lagrangian is almost fixed by requiring the anomalous superconformal walled identities of the super-Young-Mills theory, and it has the following form here. So this is the superpotential, which has this structure here. The superpotential is completely fixed by the anomalous walled identities, in particular are symmetry walled identities here. And there is a color or kinetic term here of this form, which is constructed by dimensional reasons with a arbitrary parameter rho. And this scalar potential is not fixed by the word identities, so one can add higher derivative terms here. But this is the simplest one, and it seems to be the only one which ensures that the Hamiltonian of the system is bounded from below. Now, there are some issues with this Veneziano-Yankelovich Lagrangian. It is not single-valued, as one can see. So if we just rotate the field S by the total angle, then it gets shifted by a total derivative, which is dmCm. Here. So in the Young-Mills case, this would be the instantonic topological density here. But this can be actually cured in the following way. Here we should take into account that in the Lagrangian, the field S is chiral, so it's constrained superfield, and if we take the variation in the Lagrangian, we should vary the Lagrangian with respect to the independent real prepotential U here. And for the variation to be well defined, we should introduce a boundary term, which often happens with the theories. They require the boundary term, and the boundary term has this probably not very suggestive form, but there is in superspace, but there is a procedure which I not explain how to get this term in a systematic way, but we don't need it here for our discussion. But what happens is that if we take the same rotation of S in the boundary term, then the shift of the Venetiano-Yankelovich Lagrangian gets explicitly completely shifted by the shift of the boundary term here. So let's have a closer look on the bosonic sector of this Lagrangian. So I just throw away fermions, and then the Lagrangian reduces to the following form, where there is this Kähler metric, the second derivative of the Kähler potential, the kinetic term for this three-form or one-form field. Here, and the contribution of the superpotential terms, plus the boundary term. And the boundary term in this in the bosonic theory simplifies to this expression here. So it's quite simple. Now, what we would like to do, we would like to integrate the auxiliary fields as usual, and to get the potential for the scalar field from this Lagrangian. And to do this, we should solve the equations of motion for the auxiliary fields, and we do it in the standard way. So the equation of motion of the algebraic equation of motion of the field D allows just to express it in terms of this ratio, the real part of the derivative of the superpotential divided by the Kähler metric, while the variation with respect to Cm gives this total derivative here, which one can integrate out and get the integration constant, which I introduce as n divided by 8 pi here. So this n will be quantized, and this is again related to the fact that this object in the super-Young-Mills theory is just the topological density. So it's related to instanton number here. And then combining these two expressions together, we find that the auxiliary field F is the following combination of the integration constant and the superpotential and the Kähler metric. Substituting this back into the Lagrangian, we get the potential which was obtained by Kovner and Schiffmann back in '97 using a somewhat different reasoning. And so the superpotential, you see, the potential for the scalar field has this form, and it includes this contribution of the integration parameter here, which should be considered as a parameter or a discrete variable rather than a constant. So the potential, as you can see, is single-valued, but it multi-branched in the sense that to make it single-valued, we should also change the values of n, which when the argument of S varies, we will see it. And this potential has cusps when the argument of S is equal to pi n divided by n. And from the form of this potential, we see also that this potential has minima when the vacuum expectation value of S is equal to lambda cube times the phase, the argument S is equal to 2 pi n divided by n.
Dmitri,
yes.
In your derivation where it was an integration constant, can you see its integer?
No, I should keep in mind, in general it would be
It's just anything.
standard, yeah. But if I keep in mind that this theory is an effective theory of the superrank Mills, and this quantization of n is also related to the fact that R symmetry is broken to z to n. So this, yeah. So this is somewhat implicit reasoning which requires this guy to take discrete values. Let me show how this potential looks like for the case n equals 3, and let us fix the modulus of s equal to lambda cube so that this term disappears. Then the first sector is when n equals 0, then the angle of the field S starts from 0, the argument starts from 0, then it goes, and the potential grows with the, when the argument goes from 0 to close to 1, or when it goes to the value pi divided by 3 here. So pi divided by 3 is close to 1 here. And then the value of n jumps from 0 to 1, and then the potential starts to decrease, arises at the second minimum here at the point 2. Then it starts to grow again, and then this parameter n jumps again, and the things goes until the value 5, where the argument s reaches the value of 2 pi n. And this is the same vacuum because as the vacuum at n equals 0. And you see that the potential has cusps here, so it is not smooth. And the question is what forces the jumps of these parameters here is, and the answer is that there should be a membrane sitting here which has a charge ensuring that on the left-hand side and on the right-hand side of the membrane the values of n are different. And this is what we would like to do now. So now I would like to couple to the super Young-Mills membrane in a supersymmetric and kappa symmetry invariant way. And this is what we did in our paper with Igor and Stefano. And so the action of this system has the following form. Here you see that this is a membrane tension as usual, which is equal to the membrane charge with respect to the three-form potential, which is the Vesuv inner term, and this is dictated by kappa symmetry. But then there is this another contribution here, which is the module of the chiral superfield here, which appears. If there were no this contribution, then this action would be the standard supermembrane action in 4 or 11 dimensions, which has been studied for a long time. But this contribution is new. It's, I think, for the first time it appeared in the paper by Igor Bandas in 2010 around. But for the generic coupling of membrane to a chiral scalar superfield. And it's quite surprising that nobody studied in these decades the coupling of the membrane to the super-Young-Mills, though it was the membrane was studied a lot with respect to coupling to different kinds of supergravities. And this is what we do here. So in more detail, what is Hij? Hij is an induced metric, as always, which is constructed with the use of the flat superfield binds here, because we are in flat superspace. So again, this S is the pullback of the chiral superfield, which is either composed of W alpha in the case of the super-Young-Mills, or it's just the Veneziano-Yankelovich chiral superfield in the effective description here. U is the superpotential, and this 3 form here has this structure. So it's constructed with the use of the superfield binds, flat superfield binds, and the superpotential in its covariant derivatives. And the last term here is the, if we set Grassmann variables to 0, that this is just the Chern-Simons term here. So this is why I wrote the factor 4 pi here, because K as a charge can be associated with the level of the Chern-Simons theory on the membrane. Now, let me say some words about kappa symmetry, which fixes the coefficients there. So this is a counterpart of local wall-volume supersymmetry, as we well know, and under which the Grassmann wall-volume variable theta transforms with just by a shift with the parameter kappa, and the coordinates, bosonic coordinates are transformed in this way, while the parameter kappa and its complex conjugate are related by these metrics, this combination here where gamma squared is equal to 1 and has the following form in terms of the pullbacks of the superfield binds here. The presence of this kappa symmetry allows to eliminate 2 of the 4 fermionic modes of the membrane. So we have on the membrane 4 fermionic modes, but kappa symmetry removes 2 of them. And then we also have the volume reparameterization invariance, which removes 3 of 4 bosonic variables x, so that we are left with a Galston supermultiplet, which consists scalar supermultiplet consisting of a real scalar and Majorana spinor psi. So in general, as we well know, the membrane breaks half of bulk supersymmetry, and in this case, this indicates to us that this membrane may have something to do with these BPS domain walls we are looking for. And to see that indeed there is a BPS configuration of this membrane, let's just set all the components of the Galston multiplet to 0 and see what's going on with the static membrane. Then one can easily show that the membrane action just reduces to the n equals 1 3-dimensional SYM super Young-Mills of level k, where psi's here are real components of the chiral spinor, chiral component of lambda 1.
Excuse me, Dima, but
Yes.
but you go on shell, you don't get the 2, but only 1 fermions. Is it true? Because otherwise you don't have the matching of supersymmetry. So there's 1 remaining.
Yes, but this is off shell, right? So off shell we have 2 fermions.
Okay, but on shell you have 1.
Shell, yes, to match the physical degrees of freedom, as always, there will be 1.
Okay, okay.
But kappa symmetry removes off shell.
So but you get the matching on shell then?
Yeah, on shell there is always the match. The fact that, again, that there remains only half of the fermions corresponding to the first component of lambda here is just due to kappa symmetry. Okay, now what we would like to do, we would like to plug in this action into the, or add it to the Veneziano-Yankelovich action. and to rederive the equations of motion and to see how things change in the presence of this membrane. And again, since we are interested in the BPS domain walls, and I have already shown that if we set to 0 this Goldstone sector of scalar multiplet on the wall volume, then we have some BPS state there. So we will be interested in the solutions of the system of the Yankelovich model coupled to the membrane, where the membrane is static and it sits at the point x3 equals 0. Here, then the wall volume coordinates are identified with 3 other coordinates of space-time. And if we look at the equations of motion, then the membrane provides a source, of course, to all of the equations of motion. But in particular, we are looking at the modification of the auxiliary field equation related to the 3 form or 1 form here. So now, before there was 0, but now we have the contribution of the membrane source of this form, but we can still integrate this equation. And then what we see that this parameter n requires the contribution from the membrane, where theta is the step function. So to the left of the membrane, it is 0, and we have the same value as before. But to the right of the membrane, this n gets shifted by the value of k here. And this is what happens explicitly. So the membrane just separates 2 vacua with the value of n and n plus k of the phase of the Gagina condensate here. Okay, now we would like to solve the equations of motion completely for this system, and looking for the BPS solutions of these equations. And first we should derive the BPS equations themselves, of course, and this is well known how one does it. So we consider, we require that the variation of the spinor field of the model is 0, because we set it to 0, and look for solutions which satisfy these equations. And since we are dealing with the static brane, we have an ansatz that the only dependence of the scalar field is along the direction which is orthogonal to the brane. And then this BPS equation reduces to the first order differential, one-dimensional first order differential equation of this form, where it is important that there is a phase alpha here, which is nothing but the phase of the value of the scalar field on the membrane. And this, if you remember the form of the kappa symmetry variation, this is exactly the phase which appeared in the kappa symmetry projector, which selects which supersymmetry are preserved, is preserved in this system. So more explicitly, if we substitute the values of the superpotential and Kähler potential into this equation, then the equation takes this form. And then we can study first, for example, what is the tension or energy per unit volume of this system using the standard BPS or Bogomolny calculations of the action for the BPS equations. And what we find is that the standard formula, actually, that the tension of the domain wall is the difference, modulus of the difference of the superpotential to the left and to the right of the membrane. But what is important here is that this tension of domain wall is the sum of the tension of the membrane and the tension or the energy density produced by the scalar field itself. So, and that was one of the crucial difficulties why the domain wall solutions were not identified before, because this part was not taken into account in the calculation of the domain wall tension, for example, by Kovner and Schiffman. They did not get the correct tension for the domain wall in the absence of the membrane contribution here. Okay, then the next step is to find explicitly the solutions of this equation and of this BPS equation, and this is what I would like to show you now. So we are looking for the solutions for which the scalar field through the brane is continuous, and it turns out that such solution exists for the following values of the charge of the membrane. So the the module of the charge of the membrane should be equal or less than n3, or it should be equal to k equals n here. And then we have 1/2 BPS. This corresponds to 1/2 BPS domain wall between the same vacuum on the left and on the right of the membrane. Let me show the examples just for different k and n. The form looks as the same, but for just as an example, let's take k equals 1 and n equals 3, 4, 5, 6, 7 here. Let me know that we did not find solutions, continuous solutions in this sense for the case of SU2, where k is either 0 or equal 1. So it does not satisfy these conditions. This somehow is in agreement with the fact that other people like Schiffman did not find the solution either using their methods. So let me start with the form of the superpotential. The superpotential jumps actually when it crosses the membrane. The real part of the superpotential multiplied by the phase of the scalar field on the membrane is constant here, as you can see. These different lines correspond to different values of n. So this is n equals 3, n equals 4, and so on and so forth. While the imaginary part of W multiplied by the phase is jumping here in this way. So the membrane sits at the beginning of at x equals 0. Now the form of the field S itself for these solutions is as follows. So you see that for the modulus of S divided by lambda cube, the domain wall is actually a trench. It's not a domain wall. So the value starts from 1 to the left of the membrane, and then it goes down depending on deeper and deeper, and the deepest value is for n equals 3 here, and here there are cusps. So the modulus of the scalar field is does not have a derivative here, but it's continuous, but there is a cusp here. And you see from here, you may see that why n equals 2k is not inside. Because if it happens that for n equals 2, this the value of the modulus goes below 0, which is not possible here. So the n equals 2k is excluded. And the argument of S is smooth. On the other hand, it starts from one value of the vacuum to the left of the membrane, and then grows depending on the value of n to to another value of the Gagina condensate here. This is as far as these solutions with small values of k is concerned. And then there is, as I said, there is a solution where k is equal to n. But remember that n equals 0 and n equal n vector are just the same, one and the same. They are identified because this is just the total angle which the Gagina condensate makes. And here, indeed, the domain wall is the domain wall. So the modulus of the field S grows on the membrane, and then so the shape is as follows, while again the argument of S is continuous. And so this last domain wall is actually tensionless, because if you look at the formula for the tension, because the W is the same to the left and to the right, then the total tension is 0. And so this is a tensionless object. And on the Riemann surface, the behavior of the scalar field is as follows. It starts from 1 here, then goes to the -4 value, more or less, and then it goes back to the value 1. So it makes a closed circle here. So this domain wall is on the same vacuum, and the question is whether it is stable or it just dissolves into the super Young-Mills vacuum. Okay, I think I am almost done with my presentation. Let me just conclude and then say some words about outlook. So what we have done, we have constructed a supersymmetric and kappa symmetry invariant action for the membrane, describing its coupling to the n equals 1, d equals 4 super Young-Mills, and its Veneziano-Yankelovich effective description. And we have shown that the presence of the membrane changes and separates two different vector of the super Young-Mills theory. And we found that the computed explicitly the tension of the BPS domain walls interpolating between these vector, and found explicit solutions for the following values of the membrane charge with respect to the number n, of the dimension of n of the super Young-Mills gauge group here. This, as I already said, that for k equals n, the domain wall, interestingly, we have found 1/2 BPS domain wall, which is, has a 0 total tension. So the tension, the contribution of the membrane itself to this 0 tension is positive, and the contribution of the scalar field is negative. So it's a kind of the contribution of the scalar part of this configuration is like orientifold plane in some sense, that cancels the charge of the membrane. Okay, I'm almost done, but I think I should justify why I'm giving this talk at the workshop, which is dedicated to M theory. So let me say some words about the perspective on these super Young-Mills domain walls, which people have from M theory and type 2 A-string theory. So Witten actually suggested that if we lift the n equals 1 super Young-Mills to M theory, then the domain walls of the super Young-Mills should be described by M5 branes wrapping 3 cycle of G2 halonomy manifold in in M theory, and later Acharya and Waffa developed this description using the type 2A structures, and they used a stack of K D4 branes which wrapped an internal two-cycle with n Ramon fluxes in type 2A theory to construct an effective theory, volume theory on these domain walls. And what they got is that using this construction, that the theory is n equals 1 super-Young-Mills plus Chern-Simons theory of the group UK and the Chern-Simons level n here. Then, by integrating the massive modes in this theory, one can reduce it to a pure topological Chern-Simons theory with the group UK and Chern-Simons level n minus k for the non-abelian part, and level n for the abelian part of this non-simple group here. While what we have in our model, we have a three-dimensional volume theory on the membrane with an induced Chern-Simons, which is of group SUN and level K. So you see the difference here. And the difference here is also in the fact that since they start from the D4 branes, then on the wall volume, this Chern-Simons theory is intrinsically wall volume field here, while here we have the induced Chern-Simons on the wall volume due to the embedding. And but what happens is that at least for k equals 1, there is a so-called level rank duality of three-dimensional Chern-Simons theories developed by Seiberg, Kolmogorski, and others. And using these level rank dualities, it can be shown that for k equals 1, this model is level rank dual to that of Acharya-Waffa. But for k greater than 1, this is an open question how to relate these two descriptions of the domain walls, which I hopefully address in future. So I think I'll stop here. Thank you.
Do we have any questions? Yosha?
So if we take the membrane with boundary, and then we let that boundary end on the heterotic boundary in M theory, would some sort of reduction of the heterotic gauge theory correspond to this, perhaps?
You mean?
Take the membrane with boundary and let the boundary end on the heterotic domain wall, the M9, if you like. And there we have a supersymmetric Young-Mills, of course not the same gauge group, but some reduction.
It would be interesting to look at this. I did not know your paper. Yeah, it would be interesting to have a look.
I'm saying in general, no, in general it would be nice.
Yeah.
It's not something I did, but yes.
Okay.
Martin?
Coming back to your introduction and motivation, I'm sort of wondering how I should view these membranes. Are they something which is already exists in the super Young-Mills theory, or something that I actually have to add? I mean, are
well, depending on what.
It's sort of important. I mean, if
I
I
agree.
look for
Well,
solutions, singular solutions, do they correspond to sort of
yes.
matter, which sources which
In the
are-
pure super Young-Mills, they should exist as their own. If I think, I mean, if I don't want to add any other matter like fundamental matter to the theory, then these membranes should. To resolve this problem of the singularity of let's say, Veneziano-Yankelovich or cusps of Veneziano-Yankelovich description, I don't know another way how to do that within the super young Mills theory itself. But what happens is that if we what I was pointed out by Smilga, who worked on this topic back in the 90s. So they studied the domain walls in super QCD with fundamental flavors. And they found that if the number of flavors is less than n divided by 3, then you can take the mass of the flavor multiplets to infinity, and still the domain wall solutions survive. And it seems that these domain wall solutions are exactly the ones which I mentioned. So, from that perspective, this membrane may be a manifestation of
remnant
of the very heavy flavor modes in
right.
QCD.
But in the pure super young Mills, it's simply something you have to
Yes.
postulate in order to have a complete theory.
Yes, but in the pure super young Mills, there is no way. At least I don't know any other way to.
Thank you.
I mean, just to follow up with that, suppose I set up some experimental situation where I forced super young Mills into one vacuum over here and the other vacuum over there, right? Mm-hmm. So then there would be a domain wall. And presumably it's not an additional degrees of freedom like in M theory where there's a two-brain. It'd be more like some kind of, I don't know, boundary effect or something, that you would see degrees of freedom lying on the boundary of the, like a Hall effect or something.
Well, I don't know. Maybe there are domain walls which are not BPS.
Yeah.
That's
but then you would expect that you could derive your action from somehow the original degrees of freedom of the Yang-Mills theory. I don't know. I had one more quick question. Is you have this tensionless domain wall. I mean, is it stable?
Yeah, that's the question. I mean, it's have BPS. We know tensionless strings, tensionless brains, which classically are stable, right? But I don't know. But in principle, so this is to be studied. I think how stable it is, because in principle it can shrink just into or dissolve into the vacuum. Topologically, it is not prohibited because, as I have shown, there is this circle for the scalar field.
Although, if you had a compact direction in space-time, you might imagine some kind of winding thing that would make it stable.
Yeah.
Christian?
Yeah, probably briefly. Isn't there also a link to just Hanani-Witten configurations where I have n D3 brains and I have a PQ brain in the middle? Don't I get exactly the same thing? Up to, okay, then I would have n equals 2. I need to break it somehow down. But if I want just level K Chern-Simons, right, it's just a bound state of D5 NS5 that I need, and just a stack of n D3 brains. You get the same equations actually that you had before on the.
You mean this one,
exactly.
or this construction here?
No, the other one. The other one.
This
really
one.
Three-dimensional. So you have membrane with Chern-Simons and otherwise Yang-Mills. Right. This is what you get if you have PQ brains in stacks of D3.
Yeah, I mean the Acharya-Waffa construction, I think, can be obtained in that way.
Yeah, but you say that you get only for K equals 1. Right,
No, I mean that I don't know, because here all these constructions, and the ones you are talking about, they are D brains.
Yes.
So they carry the internal walled volume gauge fields on their walled volumes. Mm-hmm. And here is the difference. But here, this Chern-Simons is induced. It's not the internal gauge field. But here maybe I may say what is the problem, not the problem, what can be one can think about to develop this situation. So here, what I have considered a membrane of charge K, but in principle, I could interpret this as K membranes of charge 1. And then one might think of considering the K membranes of charge 1 as we do, for example, in the BLG or ABGM case when we have a stack of membranes which produce the Chern-Simons theory on bare wall volumes. And then probably this will resolve the problem also with the relation of these two approaches in the case of K greater than 1.
ABGM is precisely constructed with the NS5 and the P5. That was the construction in the original paper with PQ brand.
Yeah, in this sense, yes, in this sense, yes.
Do you have any more questions? Otherwise, let's thank Dmitri for a very interesting talk.